Con Bariloche, Argentina.
Well, until we wait for my talk, I would like to spend a couple of minutes thanking the organizers for this wonderful meeting, and especially to Pablo, that pushed all the things and transform our local annual meeting in this wonderful international workshop meeting. So thanks, Pablo, for all the effort. I know you did it hard. So
Sorry, I don't know what's happening. I'm going to look. Perhaps it's time for continue the discussion. I interrupt.
well, maybe I can start before telling you what's the idea of my talk. As probably you may know, we have been working in the last year in developing a model to explain bipolar resistive switching in complex oxides. So the main idea of the talk is to show you and introduce to you the results of our model predictions, and mainly concentrate on complex oxides. By the end of the talk, I'm going to show you some new results that we have on binary oxides, bipolar resistive switching on binary oxides. So I don't have nothing else to say. Okay. Well, as I already told you, I'm going to talk about bipolar resistive switching and elaborate on our model results. I have prepared some introductory slides, but I'm going to skip them in order to the audience. I mean, I don't need to show all the introductory slides, so that's work. Okay, I don't need to motivate. So I'm going to focus, start by here as focus to put in frame the talk. I'm going to talk mainly on bipolar, resistive switching. As most of you know, and someone also showed these transparencies, bipolar resistive switching is characterized by the kind of IB characteristics, and it's mainly observing complex and also in binary oxides. And I'm going to elaborate on these three ingredients that are the basics of the main ingredients that characterize, as far as we understand, the bipolar resistive switching, which is the existence of Schottky-like interfaces, inhomogeneities, which are ubiquitous in complex oxides, and also oxygen vacancies. So, as of course we agree that the bipolar resistive switching is a sort of interface type of switching, which is due essentially to the migration of oxygen vacancies in a narrow interface close to the electrodes. So, as I told you, I now motivate our model in these three ingredients, which is the existence of Schottky interfaces, inhomogeneities, and oxygen vacancies. So I start by showing this known also result from the review of Professor Sawa, in which he emphasized the role of contact resistance in resistive switching. As I told you, and we all know, bipolar switching seems to occur at the interface region, and it's believed that the metal oxide interface is a sort of highly resistive region in which maybe a Schottky barrier type could be formed and could be the origin of the high contact resistance that appear at the interface between the metal and the complex oxides. Also here in this transparency, it is shown how the IV characteristics turns from ohmic to highly nonlinear when you change the electrode from metal one in which the interface is ohmic from one in which, like titanium, the interface with PCMO is highly non-ohmic and shows a Schottky barrier. Also, this experiment of Ignatieff's group shows that when switching mainly occurs at the interface between the oxides and the electrodes, this is a Kelvin microscopy view of the resistance along the sample. If you follow this line, and you plot the resistance along the sample and try to follow how the change in the resistance happens along the sample when the resistance change from high to low resistance, you say that almost all the voltage drop and change occur at the interfaces, even in the low and in the high resistance states. And the bulk of the samples remains always unchanged, or essentially unchanged. So all the change of the resistance occur at the interface. So the other ingredient, which is very common from complex oxides, mainly from composition and also from the way in which the samples have been grown, maybe by pulse laser deposition or other techniques in which defects could be created even in the growth processes, and also it's known from first principle calculations and from theories of metal insulator transitions and what else, that in general all the transition metal oxides present inhomogeneities, like manganite or other LCMO, for example, it's another manganite, in which, for example, you can observe, these are two conductive maps of the sample in which can be observed different regions with different high values of conductivity. So in a way you have a sort of insulated region with high conductive regions inside. So inhomogeneities are one of the ingredients of these complex oxides and almost present in most of the systems. And of course the oxygen vacancies, which also are maybe also by composition or also with the atmosphere in which the sample had been grown. Oxygen vacancies are present in all these systems, and as you may know, the fact that resistivity in complex oxides increase when the oxygen content is reduced, because the conduction mechanism in these complex oxides is the double exchange mechanism. When you include oxygen vacancies, you block this exchange, double exchange mechanism, so resistivity increase with the oxygen vacancies content is increased. And other thing which is important is that in general the surface region of the sample has a large content of oxygen vacancies at the bulk side of the sample. So the image, that the pictorial or science art image that we get from the resistive switching in these complex oxides is that as you apply voltage, the electric field in this region moves vacancies, and the polarity move the vacancy back and forth from the interface, and this is the origins of the change from the high resistance to the low resistance state. So with these three ingredients in mind, as I said, the highly resistive interfaces, the inhomogeneities, and the presences of oxygen vacancies, we have elaborated a model which essentially is based on these three ingredients, and in which the pictorial image is the following. We have the top electrode, the bottom electrode, our sample with insulating media with some inhomogeneities, conductive regions. Most of the samples need a sort of electroforming processes in which a conductive or conduction path is created, and this conductive path will be the focus of our model. We took one of these conductive paths. We could have many of this one. The simplified and minimal version of the model is this one. We have this conductive path. We have the regions in contact with the electrodes, which will be different from the region that we call the bulk of the system. So these regions are going to be characterized by high resistance regions, okay? And the bulk of the system is going to have at least a lower resistance than these interface highly resistive regions. And of course, along this path, we are going to have, I'm going to show you here. I took one of these paths and flipped on the horizontal position, but in a way it's the same. We have the left electrode, we're going to be the top one, and the right, the bottom one. And here is the bulk of the sample, and we took one of these paths. This path is, each division is some nanometer, 10 nanometers around size, in which we have some concentration of oxygen vacancies, okay? The density of oxygen vacancies could be initially uniform, or eventually not uniform, but as we need, I'm going to show later, the forming processes rearrange the distribution of oxygen vacancies, and we need to have a special distribution of oxygen vacancies in order that the samples start to switch. An important ingredient of the model is, of course, we take one of the regions